Absolutely.
I think we are ready
You want me
to.
to do it?
So
Excellent.
just a final reminder that this meeting is being recorded and is being live streamed to YouTube. And if I could ask everybody to just mute their microphone and their video camera, John will get the meeting started just momentarily.
So wonderful. Thank you so much, Sue. Those of you that don't know, Sue is our behind the scenes person. She does an amazing job in getting all the technical stuff here set up. And then of course, along with Sue, we have Doug Turner, who is manning the emails and ready to assist anyone who needs help. And we have Chris Stretch, and you all know Chris, and Chris of course is takes care of our social platforms, and he's getting this recorded and that. And as Sue said, please be advised that we are recording this and streaming it as well. So, and for those of you that don't know me, of course, but you all do. So I'm John Govro, and I'm the chair of the HAA. And oh, thank you. Please mute your microphones. The applause is too much. Oh, please. No, of course you have muted them, and I can't hear anything, of course. Welcome to the September meeting. It's a new season here. Delighted to have you all here. We are once again, and for the foreseeable future, going to be doing Zoom meetings. But look at how well everything is going, and so glad that you could all join in. Tonight, we have a special guest speaker. We have Sean Ford, and I'll be introducing her momentarily. And delighted to have her here. After Sean, we will also be having Matthew Mannering, who, as usual, will be doing the Sky this month. And we're actually going to take a shot at giving away some door prizes. And we're going to, we'll do that mid-meeting as usual. And when that comes about, we'll talk about arrangements of getting the door prizes delivered to you. A couple of reminders. The calendar, the HAA Celestial Events wall calendar is coming along just great, right, Doug? Yes. And we are taking submissions of photos for the calendar right now. All members are welcome to, invited to, encouraged to submit their photos. Could be astro photos, could be through a telescope, could be just a skyscape, a nightscape, could be club activities, could be artwork, could be anything you like, and submit them to the calendar for consideration and inclusion in the 2021 calendar. Those go into calendar. You can email them to calendar@amateurastronomy.org. Another reminder that next month, October, is when the club's council of directors is instituted. The new council will be voted in if that's how it works out next month. Anybody who is a member is welcome to join in. If anybody is interested, please feel free to contact me. I will be very happy to answer your questions, very happy to talk it over with you. Everybody is certainly welcome. Council meetings are where, of course, we make all of this and the rest of the club's activities happen. They're a great group of people, a very friendly group of people. It's a lot of fun, and we would be very happy to have you join us if you are so interested. So please feel free to contact me directly, and I'm happy to talk to you about that. Let's see. I think that's all that I need to begin with. Am I forgetting anything? Wonderful. In that case, right now, I am, I will say this, that you can reach me just as you can reach Doug with your calendar submissions at calendar@amateurastronomy.org. You can reach me if you're interested in joining council at chair@amateurastronomy.org. And all of our emails are available on the club website. So enough of that, enough of the business. Now to the good stuff, all right? Well, since we switched over to doing online Zoom meetings, we have kept things in-house. It's all gone splendidly so far, and I've seen some wonderful, wonderful presentations. But today I'm very, very happy to have a guest speaker here tonight. Sean Ford is studying astrobiology at McMaster. You all got the invitations and saw the write-up on her there. Tonight, she is going to be talking about the field in which is in her area of expertise, an area in which she holds great interest, and that is field of astrobiology, the study of life throughout the universe. She'll do a better job explaining it than I. And by studying life in extreme environments here on Earth, it allows her to better understand how life might survive on other extreme environments throughout the universe, places like Mars, places like Titan. And I'm very keen and interested to hear what she has to say about this. If everybody were here in person, we could all give her a big round. But Sean, you know that we're giving you the warmest of welcomes. I'll hand it over now to Sean Ford.
Thanks so much. I'm just going to see if I can get my screen shared here.
So Sean, before you do this, I'm just going to ask Denise and Chris and Jim to turn off their video camera.
Okay, I can't seem to get Zoom to share my screen. Give me one moment here.
Hang on, make sure I have it. Should be set up so that you can share, Sean.
Perfect. How's that?
Perfect. Can see it perfectly.
Beautiful.
Good.
I cannot get the slides to advance.
Search for life beyond Earth. You could watch too. What's happening here?
Sorry, guys, just one second. I'm not sure why it is not cooperating.
It is quite all right, Sean. You take your time and to get it the way you like. While you're doing that, I will remind everybody that it is best to mute your microphone, which allows you the freedom to speak in your own home without everybody else hearing you and without you drowning out the speaker as well. So just a friendly reminder, if you can, to all mute your microphones.
Here, can you show me out? Where is it?
Okay. It should now be shared.
Here. Zoom? Which one?
All right, can everyone see my slides?
I can see it perfectly.
Delightful. All right, I think I've...
You let in?
I think so. Oh, that's not.
Oh, you couldn't have. Did you see yourself? Did you see everybody?
No.
Can you get up for a second, please?
I cannot.
Did he let you in?
They said they were getting.
Should I begin?
What's in behind?
If you're ready, yes. You can
All
start.
right. Thanks again, everyone, for inviting me to come and talk. It's pretty exciting since with the pandemic, all of the conferences are pretty much shut down, so I never get to talk about my work with anyone other than my supervisor. So what I'm going to be talking about is like the general field of astrobiology. I'm going to go into a little bit about what I do specifically, but for the most part, I'm going to keep to higher concept things. And then if you have specific questions about some of my research I share, please feel free to ask me about it at the end. So first, who am I? This is what I look like since I can't be there in person. I'm a third-year PhD student in earth science and astrobiology. So I'm an experimentalist as opposed to a theorist, which means I do stuff in the lab, in the field. I'm not so great with computer things like some of my colleagues. I'm interested in extreme organisms, analog environments, and cell membranes, and I'll touch on all of these things in the coming slides. And from my personal life, I'm an avid birder and collector of rocks. The rock I'm holding in this picture is not mine. It's a Martian meteorite, and I was very fortunate to go to the ROM in Toronto and get to see their private collection, which was very cool. So broadly, what is astrobiology? It's the scientific study of the origin, evolution, distribution, conditions, and destiny of life in the universe. It's a very big field, but most inquiry in the field falls under two main questions. The first is, how did life begin on Earth? And the second, is there life elsewhere in the solar system or the universe? Statistically, it is very unlikely that Earth is the only planet in the universe to have ever had life. That's just a maths and numbers problem. And if we do somehow ever figure out that Earth is the only place with life, that in itself would be an interesting finding because it means Earth is very special. However, statistically, it's unlikely, and I hope there's life elsewhere. Otherwise, I've wasted my whole life studying this. So what do astrobiologists do? We're very interdisciplinary. It means that scientists who consider themselves astrobiologists themselves likely have more than one area of expertise, or they work in teams with lots of different kinds of scientists. So we're involved in anything from theoretical physics to field-based microbiology. In these photos, it's actually me and my supervisor and some colleagues doing some sampling in a deep subsurface mine. So theoretical work in astrobiology really helps us to determine what may be possible within the realms of like physics and our understanding of the laws of the universe. And then experimental laboratory work helps us confirm this theory or to discover new realities about systems. And then finally, field work compares itself to both of these other fields and circles back to inform them both to improve the accuracy of all areas of inquiry. So it's kind of like a cyclical feedback where we all help each other to refine our fields and figure out the answer to these big questions. So my personal PhD research has projects related to both the major areas of astrobiology. In terms of the origins of life, I'm very interested in cell membranes. So specifically, I'm interested in the behavior and stability of molecules, mostly molecules that are related to membranes in some way. And I'm interested in how their behavior and stability can lead to the origin of life on Earth specifically. And I'm also interested in the boundary between biosignatures and abiosignatures. And I'll get into what those are in the next slide. And then in the search for life elsewhere, I use the deep terrestrial subsurface as a Martian analog. So I use very deep places in the Earth, and we basically pretend that it could be Mars. And I'll get into more about Martian analogs further along. So what is a biosignature? What is this word that I've used? It's any substance or phenomenon that is indicative of past or present life. This can be molecules that are made by living organisms or used by them, like DNA or RNA, lipids, proteins, and some gases like methane or oxygen. Quite often, exciting news from Mars will be detection of methane or oxygen. It also can include phenomenons such as the ratio of light to heavy isotopes of elements like carbon, but it can also include really obvious stuff, like if you found non-human technology on another planet, it would be considered a biosignature, though it would be very conclusive evidence. And one that's not often cited is actually motility. So if you see something moving on another planet in a way that does not fall in line with, say, wind or tide. So for my research, that first thing, how the behavior and stability of molecules can lead to the origins of life. Why does this matter? By examining the behavior and stability of membrane-forming molecules specifically, such as phospholipids, which are pictured here, I can better understand the origin of cell membranes, which are an essential component to all life as we know it. All living things have a cell membrane. It's important for keeping stuff in as well as keeping stuff out. And to detect these molecules, I use instruments like the one behind me in that picture. So looking at the origin of membranes, I want to know, how did the first membranes form and how did they behave? And do we need minerals present to either get these membranes or to protect them? So I create an artificial pond inside a glass flask, like in the picture. I throw in some clay, throw in some water, a little bit of salt, and the lipids. And luckily, lipids will spontaneously form spheres, vesicles, when they hit water. This is a great property. It means they basically become the husk of a cell without me having to do too much. And then I can subject this flask to harsh conditions. I can make it hot, I can make it acidic, I can blast it with UV light. And by adding or not adding clay, I can determine whether clay protects lipids and vesicles and the stuff inside of them from harsh environmental conditions. So that's really great. I can determine the survivability of these molecules. But one of the things is if you could go back to before there was life and you detected lipids, you might think it's a biosignature. You've detected something that tells you that life is there. But we know a lot of molecules that are implicated in life can be formed without life. So that leads into the next area that I work on, the boundary between biosignatures and abiosignatures. So an abiosignature is a molecule that life uses, but can also be made without life present. So I analyze materials where life should be or should not be living, and I look for biosignatures in these places. And this really helps us to answer questions about reliability. So how do I know I can trust biosignatures? If I get a sample from somewhere weird and I do an analysis and I find a lipid, how do I know I can trust that that means there's life? Like I said, many biosignature molecules are produced abiotically, which is in the absence of life, and this causes lots of false positive life detection. So by searching for biosignatures in places where I would expect not to find them, I can refine our ability to successfully detect life. And this is really important because we do sometimes find these biosignatures where there is no life. The big example is in meteorites. We find lipid-like molecules. We found nucleotides, which are the building blocks of DNA. We found these things in rocks from space where we know there is no life on these little meteorites. So here's an example of an experiment that me and my colleagues have been running. So clay, specifically bentonite clay, can be compacted so densely that no microbial life is able to grow. So in that panel A, that's a pressure cell and it's full of clay. And this clay is embedded with microbes, and we leave them in the ground for intervals of 2 years under great pressure. And then at each 2-year interval, we analyze for lipids. So that means I've been working on this project since 2015. I did some samples in 2017 and in 2019. And so hopefully, if all goes well, I'll get the final data point next year and we can write a cool paper about it. And what's so cool about this is you put bacteria in, and at the end, you look for what's left over of their lipids. This gives us an abiotic rate of lipid degradation. It tells us how long these molecules that came from life will last in the absence of life. And this is important because if life is present and active but not replicating, it will eat up all of the lipids around it that it can get because they contain phosphate. And phosphate is one of the limiting factors in a lot of life on the planet. If you don't have phosphate, you can't make lipids, which means you can't make cell membranes, which means you can't live. So if there's no life around, how long do lipids last? And that's the thing I'm trying to test. So once I know all this and I have a better understanding of the reliability of my detection ability to find life in weird places, how do I look for life beyond Earth? I don't have a lot of money in my lab, so we practice on Earth in analog environments. So these are places on Earth that mimic an environment found on another planet, such as Mars, and can also include environments that mimic other moons, like looking in icy places is like looking on Enceladus, for example. So Martian analog environments are generally those that are considered very extreme. They're very hot or very cold, very dry, which means there's little available liquid water. And quite often they're very salty, and they're very isolated, which means they have no access to the surface processes of the planet. So this is like, you don't have any access to rain, the hydrosphere, and you don't have any access to the photosphere, which is the sun. And those two things are big drivers of life on Earth. So my third major project is the deep terrestrial subsurface as a Martian analog. So the deep terrestrial subsurface is anywhere on the continental Earth that is below the point at which you have interaction with surface processes. So this, for me, usually means about 2 kilometers below the surface. So this part of my research involves going into the field to collect samples as part of an interdisciplinary team, which also includes people from tons of different institutes from different countries as well. And then I bring back samples to the lab and I look for microorganisms living in those samples using instruments like the one pictured. So when I think about the deep terrestrial subsurface, the questions I have are what lives there, how is this life distributed, and how are these organisms living and surviving? By answering these questions, I can better understand Earth's biogeochemical cycling, both in the past and in the present day, because microorganisms have a huge impact on our global cycles. And as I mentioned, the deep subsurface acts as an analog to potential extraterrestrial biomes and may even represent biomes that could be present on Mars today. So how I do this is I go to Timmins, Ontario, to the Kidd Creek mine. Inside this mine, there are hypersaline waters. So that means they're very salty, in this case, 10 times saltier than the ocean. And I get in a truck and we drive down to approximately 2.5 kilometers below the surface to where these waters are gushing out of boreholes in the rock. And previous work by my colleagues found that these rocks, or the water in the rocks, may be as old as 2.4 billion years. That means that the time that this water infiltrated the rock and got trapped was during the Precambrian. And I filter these waters to collect any microorganisms living associated with them using big stainless steel contraptions like the one in the photo. And I use a combined analysis of genetics and lipids and the isotopic signatures of these lipids. And I was able to identify microbial communities living associated with these waters. And it's important that I say associated. This analysis doesn't let me determine if these microorganisms came from the water, i.e., they are super old, but it does bring out the possibility that these organisms are descended from communities that have been isolated from the surface, from the air, from everything for the last 2.4 billion years. And what this research has shown us is that organisms can and do survive in the extreme environments of Earth's subsurface. And this indicates that perhaps organisms like those on Earth could survive beyond our own planet. So looking beyond Earth, by understanding the production and behavior of biosignatures in these analog environments, in Timmins or in other places on Earth, we're able to apply this knowledge to uncrewed and future crewed space missions. We learn first what is best to look for and what gives us the most reliable answers, so that when we go to Mars or we go to Titan or anywhere, we know what is best to look for. We don't waste time or money or resources. And if we learn how life could begin on Earth, we might be able to determine how it may have arose on Mars, as we do have fairly similar geologic histories. So that's the end for my specific research, but there is so much going on in this field, I couldn't help myself but to show you some cool missions. So going to Mars, the Mars 2020 mission is the Perseverance rover. It launched this past July and will arrive next year in February on the 18th. This is a special rover mission because it has a primary mission rooted in astrobiology. Previous rovers have been more focused on geologic missions that have only tertiary or quaternary astrobiology relations. So this rover, the Perseverance rover, its primary mission is to go to the Jezero crater and look at the geology in order to assess past habitability. So that is whether or not this environment could have ever supported life as we know it. It's important to remember that it's not looking for microorganisms. What it's going to do is the step before that. There's no point in looking for microorganisms if it was never habitable in the first place. So first, this rover will determine if a climate existed with enough time to allow for life to exist. So the next mission I want to talk about is the Hayabusa 2. This is a mission done by JAXA, the Japanese Space Agency. And this is a sample return mission from the asteroid Ryugu. And this is a cool mission because they used an explosion in space. And basically, NASA would never allow this because of safety. Explosions are generally not a great thing to do near your multi-million, billion-dollar spacecraft. Things can go very wrong. But what they did is, this little animation will show you once it resets. The Hayabusa 2 let go of a detonation or a charge and then hid in the shadow of the asteroid as it exploded to avoid the shrapnel of that explosion, which is just brilliant. And then it's able to touch down and grab a sample of the subsurface material. So the point of this mission is to look at the evolution of organic matter through the solar system history, which will help us understand the origin of biogenically important molecules, which may have been used by the first organisms on Earth. One of the biggest hypotheses for how life may have began includes bombardment by meteorites that contain organic molecules that then end up on Earth and are able to assemble and become a living system. So JAXA has been really great and has posted some cool videos. So I actually have an animation of that touchdown moment from space. So it lowered to the surface and just touched the asteroid very briefly, and that was sample collection. It was very quick, it was very elegant, and it's just so cool that we have this video from space. So for the final mission, I want to talk about Titan, because this is just such a cool place and such a cool mission. So Titan is the largest moon of Saturn, which I'm sure most of you know. It's special because it has a dense atmosphere made of 97% nitrogen, which is similar to Earth, though it does have some nasty stuff in there, and no oxygen for us. And no other moon in our solar system has an atmosphere like Titan's or nearly as substantial as Titan's. It is slightly larger than our own moon and has very low gravity relative to Earth. And this is important. If you were on Titan right now and you had two big pieces of cardboard, you could flap them with your arms and you'd be able to fly. That's how low the gravity is and how dense the atmosphere is. It has a rocky interior, which is covered in a layer of complex ices, which then is followed by a subsurface high ammonia water ocean, which is then encased in different ices. And interestingly, there may also be liquid methane on the surface, so lakes of methane. So the mission that is going to Titan is the Dragonfly mission. The pictures on the left are from the Huygens landing site, which is the last mission that was specifically going to Titan. It descended through the atmosphere and took these photos. So it goes from in the atmosphere at the top all the way down to just over half a kilometer above the surface. It took this series of photos, and they look a little bit warped because it is a circular image that's been flattened for this. So Titan is an astrobiological analog for the very early Earth. And the Dragonfly mission that's going there is an absolute marvel of modern science and engineering ingenuity. They are sending a car-sized drone to Titan, and it will fly and hop from site to site along the surface. And like I said, flight is possible due to the low gravity and the very dense atmosphere. And the Dragonfly mission is part of NASA's New Frontiers project, which means NASA chose this mission from two finalists. The other finalist was the Caesar mission, which is also really cool. They were going to bring a comet sample back from the comet that was explored by Rosetta. But basically, NASA gives them up to $1 billion to fund this mission, and then when they're all finished, they buy them a rocket and shoot it off into space. And I was very fortunate last year to be in Seattle at an astrobiology science conference when the winner of the New Frontiers mission was announced as Dragonfly, and a whole bunch of people from the mission team were there. And the way New Frontiers works is that no one knows who's going to win until they announce it. So no one on the team knew that they were going to win. So there was lots of champagne and crying, and it was wonderful. And so just finally, I have this video, which I hope is going to play. It is. So this is the concept video for the Dragonfly mission. It descends through the atmosphere, is released from its parachute, and is able to fly immediately. It will head down towards the surface, do a little bit of reconnaissance as far as I understand, though this is obviously just an animation showing the capabilities. And it will be able to land wherever the scientists tell it, and then relay the information, photos, etc., back to Earth. And so that is everything I have. Thank you very much. And if you have any questions, I'd be happy to take them.
Sean, that's absolutely marvelous. Thank you very, very much.
You're welcome.
That's fantastic. I'm sure there will be other questions, but you know, host prerogative here. I get to go first. So first of all, totally jealous of the places you've been and the experiences you've had. Totally envious. Being at the ROM, remarkably, you can verify this. Has one of the largest Martian meteorites in the world.
They do.
Which is quite remarkable as you walk through the ROM's rock and mineral display, and there are all kinds of extraordinary, beautiful, artistic specimens, and this entirely uninteresting looking rock sitting there turns out to be one of the most amazing things there. And also on a gram for gram value, probably one of the most valuable ones there, being from Mars. And look at you holding that Martian meteorite in your hands.
Yeah, it was a really weird experience because like the people who work there are kind of desensitized. So we were going there to talk with a woman named Kim Tate to discuss some collaborative projects. And they just take us back to like show us stuff, and they just put this stuff in your hands, and you kind of feel like, am I allowed to touch this? Isn't this like not for me? I'm just a grad student. But they let you touch everything. They're like, yeah, here, this is a lunar meteorite. Like this is from this outer place in the solar system, and it feels like I shouldn't be allowed to touch those things. Absolutely
marvelous. So you talked about how the the exploration of this could lead to two possible outcomes: finding life and not finding life. Mm-hmm. And of course, there's the famous Arthur C. Clarke quote, right? That says, Clarke said, the two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. And they are. And he nailed it. So with all of this, all of these wonderful possibilities, where are you placing your bets? Where would you like to see explored? What's closest to your heart?
Well, it's actually funny you asked that. It's in my thank you slide background. If I could look at anything and money were no option, I would look at the system in this picture, which is the TRAPPIST-1 system.
Yes.
So I'm sure as astronomers, you're familiar with TRAPPIST-1, but it's such a cool system. It has so many rocky planets in its habitable zone. And I just think it's such a great target for astrobiology. You know, I'm really hoping that the James Webb Space Telescope will be able to show us some cool stuff in this system if it has time booked for observation in that area. But if I have to stay in the solar system, I think the subsurface of Mars is a really good place because we do know that Mars at one point was warm and wet and very like primordial Earth-like. And if there is anything still alive on Mars, it'll be in the subsurface. And likewise, the evidence of anything living in the past will be in the subsurface. Without a appreciable atmosphere and just being, and no magnetosphere and being blasted by solar radiation and winds, there's not a lot of direct evidence you could find on the surface of Mars. It's been whipped all to heck. So you'd really have to drill quite deep. And unless you can get giant drilling machines there, the subsurface of Mars will be difficult to look at.
Marvelous. Thank you so much, Sean. Absolutely wonderful. I am very happy to hand it over to anybody who has any questions for Sean.
John, I'm going to ask Sean if you can stop sharing your screen so that we can see the participants.
Oh, yes, of course. I forgot I had control of that.
That's okay.
There we go.
And if anyone would actually like to ask a question, they can turn on their mic and their camera if they would like, and ask Sean a question. Matthew?
Yes, I was wondering if on Mars it made the most sense to do subterranean exploration using the natural accesses to the lava tubes that are there from some of the big volcanoes.
Yeah, absolutely. You're so correct. The easiest way to get into the subsurface would to be use natural cave systems that are created by those old volcanoes. The only problem with that is it's really hard to drive a drone into a Martian cave if you're not there to do it. But I know that there is a project with NASA called Basalt. The postdoctoral fellow in my lab works with this project, and she spent a whole bunch of time down in Death Valley practicing as like pretend rovers and pretend astronauts to like drive drones and things in between these like really pointy, sharp rocks. And it's definitely feasible, especially if you had astronauts on the ground. And you wouldn't have to drill anything then if you could just go in through a cave.
That's it for me. Thank you.
Thank you.
I'm
Anyone else?
just going to check the chat. Brett, you have a question. Would you like to turn on your mic and ask your question?
Yes, thank you. That was really great, Sean. Thank you very much. My question is relating to historical experiments that took place during the Viking missions. What do scientists now think about the design and execution of the missions that happened during the Viking landings?
Oh, yeah, that's a great question. I think probably one of the biggest things we learned from the Viking landings, man, at least in terms of like what we do today, is probably that if you get a non-detection, it's sometimes worth it to go back and check again as technology gets better. Because if I remember correctly, Viking said it found no organics present, but it turned out that it had detected organics in the sample, but dismissed them as something else. I also think another thing that Viking brought to us were lots of pictures that on Earth scientists, geologists especially, and microbiologists could look at and compare them to Earth structures. I know that there's lots of cool examples of pictures from Mars that include like roll-up type features, which looks like the Earth has flipped up on itself and rolled up kind of like a carpet. And we know that microbial mats do that when they dry out. So
Thank
I
you.
think it basically just informed us to not give up.
I think that one of the things is that they were in a big rush, and the fact that they got there with both missions and put both landers down, and then, oh, now we're here, we have to do the science. And the science experiments had to be thrown together it was a different time.
It really was. And yeah, it was a bit more Wild West space days, right? Like NASA is like very careful now, you know,
Mhm.
with so many things that have gone wrong, you know, both in the loss of human life and the loss of space missions. Yeah, I guess we've also learned a lot of caution as well.
One of the things was a visit to the old McLaughlin Planetarium when the mission pictures were posted while we were waiting to go see a planetarium show. That was a very important moment in my science life
Mhm.
as a young person.
Okay, thanks, Brett. We have a question from Jeff. I see that your hand is up. Would you like to turn on your mic and ask your question?
Hi, I was wondering if you could talk a bit more about how you check the water. So you were talking, you went to Timmins in the mine, you're looking at the water that's
Mhm.
potentially almost 2.5 billion years old. Can you talk a bit more how you check that and
Yeah,
how
so
and uh, how much you're worried about, say, contaminants that have seeped in from wherever else?
mhm. So I personally am not part of the team that did the aging of the water. That's Barbara Sherwood Lawler's group in the University of Toronto, and they use the isotopes of noble gases to determine the age. Because that water has been isolated from our atmosphere, they can do a comparison of what those ratios should be today and what they would have been when the water infiltrated. So that's how they do that. And that's pretty much all I know about the aging. It's a very difficult inorganic isotope chemistry, which is totally beyond me. But in terms of contamination, we are constantly thinking of contamination. That's a very good question. We have to check and check and check and think of all possible places we could get contamination because it is an active mine, right? As we're working, there are pieces of machinery driving by, you know, we're on a level that's no longer active, but you got to get stuff down there, right? So basically we do everything we can. I've sampled the mine service water. I've taken scrapings off the walls of the like around the boreholes. I have extracted just plain filter material. I've done everything to try and minimize my own personal contamination. And anything we bring into the mine comes either wrapped in tinfoil, and we've previously burnt it in a muffle furnace at about 450 degrees Celsius for 8 hours. And if it can't be combusted like that, we've quadruple washed it with a cocktail of solvents.
Thank you.
Yeah.
So
Sean,
Sean, sorry, Sue, may I?
Yeah,
So-
I was just gonna say, we've got a couple of hands up and another couple, there's a question in the chat.
Oh,
So,
then by all means, go for it. Yep.
okay. Sean, this is from Douglas Curry.
Mhm.
He asks in the chat, what do you think of the possibility that ultraviolet absorbing layer in Venus's atmosphere would be due to the presence of some native microbes, especially since I heard scientists haven't been able to match a chemical with the properties of this layer in Venus's atmosphere? Also, what mission do you think would be good to explore it?
Oh, that's a great question. Venus is such a weird planet. It is also an astrobiological analog because it kind of represents a very old Earth because it is further in, and as the solar system evolves, all the planets either move further in or move further out, depending on what kind of star you have. And so as the sun has evolved and as our solar system has evolved, Venus has like moved inwards. And I think what you're talking about are the like weird dark patches in Venus's atmosphere that do this weird absorption of the ultraviolet light. I'm not sure if it's microbes. It's a possibility. We have microbes living in our own atmosphere. I think The best way to probably check, I think, would be some kind of, you probably can't do a lander because it would just get annihilated on the surface. You'd probably want to try and like dip through the atmosphere. I know that on the ISS, sometimes they put like sticky panels on the outside of the space station to catch stuff. So I don't see why you couldn't have a thing that dips through the atmosphere that has adhesive pads, and then you flip them back inside the craft to where they're protected and then bring them home. So I think you'd have to do a sample return from Venus if you wanted conclusive answers.
Sean, we have time for one last question from Jim Walmsley. Jim, if you want to turn on your mic and ask Sean your question.
Yeah, you were showing pictures of that beautiful Mars meteorite, and I know the ROM has probably one of the largest ones. I have probably the smallest meteorite from Mars ever found in my small collection of meteorites. And I was just wondering, are there meteor falls that are being studied for possible life that's landed on Earth?
Yeah, so meteorites are a big focus in astrobiology, especially for origins of life stuff. I think the amount of evidence it would take to prove that a living organism came from a meteorite and survived entry would be, pardon the pun, astronomical. So I think the value of meteorites is definitely in what compounds they are able to bring to Earth, and our focus is generally on carbonaceous chondrites. There is some work with iron-rich meteorites as well, but generally we're interested in the carbon-rich chondrite classes of meteorites, and obviously the Murchison meteorite is still a huge piece in astrobiology. As instrumentation gets better, we go back and we analyze these types of meteorites. And the reason Murchison is so good is because it landed in the winter on a frozen lake and was picked up, I think, within hours. And that really is the most pristine sample you can get. A lot of the meteorites in the ROM's collection actually come from Africa. Because if you're walking through the desert and you see a large black rock, it probably came from the sky because there aren't any large black rocks there. And the problem with finding meteorites in Africa is they change a lot of hands before they get to you, and the sun essentially bakes their surface, and UV light is incredibly destructive to most of the interesting molecules. And the best other place to get them is Antarctica, but as you can imagine, it's a pretty big pain to go to Antarctica to find meteorites.
Yes, my sample is a tiny, tiny, tiny little chip from Antarctica.
Well, that's really
it's so
cool,
small
though.
you could barely see it.
Okay, John?
Sean, that's absolutely wonderful. So Sean, you mentioned that, of course, next year you'll be retrieving your clay sample, your third batch, right?
Yep.
And then what happens after that? What does the future hold for you?
Well, actually, this past year, I did one of the biggest PhD milestones. We write our comprehensive exams. So basically from here all out, it's research for me once the lab opens back up. And I'll be focusing mainly on analyzing samples from really salty places to compare to the stuff from Timmins, as I'm also interested in how super salty waters from underground might compare to super salty waters from the surface.
Wonderful. Sean, I cannot thank you enough. And I know I speak for everyone in telling you how fascinating this has been. We couldn't have made a better choice in inviting you here to join us tonight. I know everybody shares that enthusiasm. I can tell by the questions that that you got, and I know they talk your ear off for the rest of the night if I let them. So Sean, thank you so much for your presentation this evening. An absolute delight. Well done.
Oh, thank you very much. I'm so honored to have been invited. This was absolutely wonderful experience. Thank you very, very much.
Our pleasure, believe me. Everybody, of course, the evening isn't over for us. We have Matthew Mannering with The Sky this month coming. And as promised, we have door prizes to give away. And there's Maya. Hi, Maya. How are you? So now we have 3 door prizes to give away, and Maya is, as usual, is going to be the person who selects our names and gives them away. Now, what we can do is each of the winners can contact me directly and speak to me, and we'll arrange a way to get this into your hands, either through delivery or pickup or something like that, okay? So the thing to do, all right, if you find yourself a winner, the thing to do is to contact me directly, okay? chair@amateurastronomy.org. And tonight we have, I hold the prizes in my hand. So we have 2 volumes and then something a little more interesting as well. We have the near ubiquitous Astronaut's Guide to Life on Earth by Chris Hadfield. So right there, a nice hardcover edition, beautiful new book, lovely. Of course, everybody knows Chris Hadfield, famous Canadian astronaut. So we have that. We have The Glass Universe by Davis Sobel, and The Glass Universe, how the ladies of the Harvard Observatory took the measures of the stars. This is a period of time in an area that's particularly of interest to me. I love this story here. Absolutely wonderful. The Harvard calculators, who did a collection of women who did an extraordinary amount of research and work. So we have that, The Glass Universe, and from our friend Ray Watts, meteorite dealer and collector, we have 28.3 grams of unclassified Northwest Africa, possibly a chondrite. Yes, we're talking about a meteorite, folks. Here we go. I'm going to contaminate it. So there we go. 28.3 grams of meteorite right there. Okay, is going into somebody's hands tonight. Now, as I understand it, Maya, how you doing? Can't hear you, Maya. Now, as I understand it, what has happened here is Maya has accumulated the names of everybody that has logged in tonight, and Maya is going to randomly choose 3 off of the list. I don't know the method in which you managed to randomly select the 3, Maya. I don't know how you did that over there. And unfortunately, I can't hear a word. Can anybody else hear?
Hear me now?
Yes.
Yay!
Yay.
Okay. It was a speaker. We had a speaker plugged into the computer. It was that. Anyway, so the method of which we have chosen the names was we actually rolled 2 of my dad's Dungeons and Dragons percentile dice. And whichever number we rolled, the person on the participants list who was that number won. So like if we rolled number 25, whoever was number 25 on the list was the winner.
Excellent. that sounds as fair as can be. So wonderful. All right, so who have we got? Who's our big winners tonight?
For our first winner, we have Mario Carr.
Mario, fantastic. Mario, are you here with us? Mario, you want to speak up?
John Mario's not with us at this moment in time. He was here earlier, but he's not here right now.
Oh.
Do you want me to roll again?
So what? So what do we do if we had been there in real life and Maya had pulled a ticket and the person who had the ticket had left? We would have to pull another ticket. So
I will roll again, I guess, then. Okay. Number eight. Let's see. Who is that? One. And to catch.
oh, wonderful.
Me?
Yep.
Yay. What do we
And
want?
to catch. Well done. Good for you.
Do we get to
And-
pick first?
Pick first. What would you like, Anne?
The meteor.
Of course.
I should say the meteorite.
Great choice. That's what I would have chosen.
And to catch meteorite, all yours, 28.3 grams. So,
Yeah.
so good. Yep, 28.3 grams. Good for you. Wonderful. All right, Maya, who's up next?
Our next winner is Jeff Wozniak.
Jeff.
I guess I'll take the book on, I can't remember the name of the glass one. What was the title?
Oh, The Glass Universe.
Yes, I'll take that.
Yeah, great choice. Excellent. Good stuff, Jeff. And Maya, who's third?
Our last winner is Peter Wellesley.
Peter. Peter Wolseley, astrophotographer extraordinaire.
Oh, Mario's back.
So excellent. So what? Mario's back?
Yeah, in the chat.
Oh, I'll find something for Mario then, okay?
I'm here. Oh no. Oops.
Okay. I'll find something for Mario. So all right. So Anne, Jeff, Peter, and Mario, all of you want to get in touch with me and I'll arrange to get these goodies into your hands. So, and a big thank you to Maya. Well done. I like that you went classic old school with the roll of the dice. Fantastic. So well done. And that's Sheffield. All right, excellent. So good. Thanks, Maya. And congratulations to the winners. Matthew, are you ready?
I am.
Excellent. Then of course, at this point, I'm going to hand the stage over to Matthew, our observing director, who has another installment of The Sky This Month. All yours, Matt.
Thanks.
And Jim and Berna, if you could turn off your video so that Matt can take over the screen. There you go. Thank you.
Am I good there?
Yeah, I can see it, Matthew. You look good.
Yep.
All right, so off we go. Welcome to The Sky This Month. And for this month, I thought I'd start with our newsletter, The Event Horizon. It's been in the club, as a part of the club since the very beginning. And if you're interested in looking at the older editions, you can get a feel for the history of the club and a lot of ideas about hardware or just even what's up in the sky. So I can heartily recommend it. And Bob Christmas has been the editor for about 5 years and has done a great job. He always makes it look really nice and professional. And I appreciate his work. And it's his picture on the front of the event horizon this month. And it's, of course, Neowise, the comet that was in the sky a little while ago. I remember when he took this picture because there was about 15 of us there at about 3:30 in the morning on the escarpment, looking over the bay, taking pictures of the comet. And it was a great comet, first one in years, where you could see an actual tail. It was naked eye. And in my binoculars, the tail extended somewhere between 5 and 7 degrees, depending on just how good the sky was. So had a lot of fun, looked at it when it turned into an evening comet, when it was going up past the Big Dipper. And it was just kind of nice to just walk out the front door and see a comet. And there are lots of pictures of the comet in the event horizon this month. How come my thing doesn't work? I've done this. What's going on? Hang on, now mine's not moving. Can't move. Well, I've got some sort of technical hiccup here that I haven't had before. And it's not moving.
Of course, this is one of those situations where it works perfectly in practice and then doesn't work when it's needed to. Understandable.
Interestingly, I can't even exit the screen. Your screen sharing. Stop share. It's all there. It's all good. Why can't I move it?
Matt,
Escape.
Is it a
Try-
PowerPoint?
Yeah, it is.
Or did you try hitting the space bar?
Yep.
Hmm.
Yeah. I've done this lots of times.
Yeah, try unsharing your screen
Yeah.
and then
Yeah.
retry it again.
Yeah,
Okay.
unshare, reshare.
All right. Hang on a minute then. And look at that. My computer's gone wacko. I know. I thought it's still on. Let's kill that. Close all windows. Okay, I'm going to try and restart it. And slideshow from the beginning. And then go back down here. What's going on, Janice? I have no idea.
How did Sean fix hers?
I don't know. Sean, did you have the same problem? Are you still here? How did you fix yours?
I am still here. I closed PowerPoint presentation completely. And the mistake I was making was I was minimizing the like presenter view of PowerPoint.
Oh. Okay, so I had it minimized. All right, well, let me try again. I'll try the screen share again. And I'm not bringing up. What? It's not. Start Zoom. I don't even have Zoom. Sue, am I still on Zoom? I presume I am.
You are. I can
You
hear
are.
you. I'm not exactly sure. I'm going. Doug, do you have any ideas for troubleshooting from Matthew? I haven't come across this problem before.
No, but the issue I was having earlier with the screen not showing anybody has returned. So I'm wondering if there's something up with the current version of Zoom that I'm using.
I don't know. Mine's probably a couple of months old. I don't have the current version on.
Zoom just had an update recently, like in the last couple of weeks. But you should still be able to share the screen. We can't even see your PowerPoint at all now, Matthew.
Okay, let's try this again. Share screen. Screen. I need Do I need to tick off share computer sound?
Yeah,
Let's try that. Go to share. Should see my lap or desktop now.
yes.
Yep.
All right. Slideshow from the beginning. Yay. Okay, here we go. So we were talking about the event horizon, and I was actually finished with that and trying to get to this slide. So we've had a few people send me pictures this month, planetary and lunar, and Joanne's been very busy improving her skills, and she sent me this picture of Saturn. She's using a 5-inch Schmidt Cassegrain and a planetary camera. And what's nice is you can make out the Cassini gap there and some of the banding on Saturn. So that's really nice. Jeff Moore's been doing this a lot longer, and he has an 8-inch Schmidt, so he gets a bit more detail out of it. But the Cassini gap's very, very evident there. And also what's really cool is the shadow of Saturn against the rings. And if you use your telescope and have a look and the seeing is relatively steady, you can see the shadow of the planet on the rings. And something similar to that is with Jupiter. You'll be able to see pretty shortly, I would think you'll be able to see some of the moons come from behind the planet and then disappear into the planet's shadow. So you'll see it for a few minutes and it'll disappear again. So that's something to look for in the immediate future. So I mentioned the Cassini gap twice, so I thought I better mention Cassini. He was the first director of the Paris Observatory. And in fact, there's a street right in front of it is named after him. And if you walk down that street, you get there and there's the observatory. He was the first of 4 generations of Cassinis that ran the observatory, one after the other. And at least 2 of them were born at the observatory. So I guess it was really important to them that there was no Cassini gap between any of the people running the observatory. And that's my bad joke for the day. Okay, so Joanne also had a look at Jupiter, and that was at the end of July. And what's really nice is you can see the shadow of Io there on the surface, and you can see the great red spot and Ganymede and Europa in the distance there to the right. A week later, exactly a week later, Jeff was back at it again, and his picture looks very similar because, well, it is. It's just a week later, and he got Io's shadow, the great red spot with what I call the eyebrow now over the great red spot. It's quite distinctive, and Ganymede off here to the left. And that's a really nice shot, starting to see some detail in the equatorial bands of Jupiter. We had the Perseid meteor shower of 2020, except nobody was there because we had to cancel the event, but the meteors were there anyway. So we were at Inverhuron Provincial Park, Janice and I, and she was doing wide field astrophotography, one shot after another, and happened to capture the second best Perseid that we saw the whole week we were away. It left a nice green vapor trail after it disappeared, and you can see it along the left edge here. Also in the image is Saturn and Jupiter, Altair, Vega, Deneb with, of course, Cygnus in here. So a really nice image. And actually, I didn't even stack this. It's one JPEG. And I just stretched the image and just intensified the color just a bit. So it actually came out really well.
Is that light pollution from the power plant?
No, actually, we're facing the wrong way. The power plant was behind us. There's a little...
In Cardin, it's worse.
Yeah, that's true. That's true. But it's actually really nice there. You're right on the beach on a huge parking lot. There's nobody around generally, and you've got the whole sky and the whole parking lot to yourself. And we stay till 2, 3 in the morning and then pack up and go back to McGregor Point half an hour up the road to go to bed. So we're tired by 3:30 or so. We're done. This particular image is just from spaceweather.com, and I try and pick Canadian images if I can off there. And here's a great Perseid, and I think she's cheating because she uses mountains in the foreground and we just don't have that. So I think she has a slight advantage. But anyways, beautiful image. Joanne also gave a shot at doing lunar astrophotography, and I think it's her first go at it. And she sent me about 4 images. So I thought I'd name some of the craters. And this one is of Copernicus. It's one of the biggest, most beautiful craters on the moon, and generally right around the day after first quarter is when you want to look for it. It'll be right near the terminator. and it has great steps around the edge of the crater, and the ray system is very complex, and there's all kinds of tiny craterlets from when the ejecta came and then settled back down with a thump. So it's one of my favorites to look at. You can spend a long time looking at that one. Copernicus, by the way, was one of the last great visual only astronomers, visual as in no telescope. He used a quadrant, and he took thousands of observations over a lot of years. He was very, well, he wasn't a nice guy anyway. That's the main thing. And he was very fixated on what he was doing, but his observations at the time were the best in the world. Here's a picture with Tycho, which is of course one of the youngest and beautiful craters on the moon. It's got the great ray system with the rays extending halfway across the moon or even more. If you look at Tycho itself, it's got very sharp walls. It's got a great central peak. And just down to the right there, you can see I've marked Clavius, which is actually one of the really large craters on the moon, but you're seeing it foreshortened because it's near the limb. And one of the ways to really easily identify Clavius, if you find Tycho, is look for all these craters that make this like eyebrow effect hidden here inside. What bigger, smaller, and see how many you can count within Clavius. So Tycho is named after Tycho Brahe. He was another guy who accumulated tons and tons of data. He was a party animal, and he had a brass nose. Now, lots of people believed for the longest time that it was a gold nose, but apparently they've dug him up twice in the last 20 years and run some tests and figure now that it was actually a brass nose, which would actually go with his rather brassy character. And Clavius was a German Jesuit priest who I really believe did a lot of recording of things, and he was a mathematician and an astronomer. So here we are with another one. Pythagoras, of course, is known for Pythagoras's theorem. He's a mathematician from centuries and centuries ago. Sinus Iridium is translated as the Bay of Rainbows, and Mare Imbrium is the Sea of Rain. So you've got the rain and the rainbows. Leverrier is a really interesting guy. There he is on the right in front of the Paris Observatory. He hasn't moved in a long time. He actually calculated the orbit of Neptune and calculated where it was in its orbit, sent the information to a guy in Germany who started looking and found Neptune on the first night. So Leverrier obviously deserves a crater on the moon, and because he did a lot of great work for astronomy. Laplace was one of the great polymaths of all time, and I think he got shortchanged because all he got was a little mountain at the edge of Sinus Iridium. But if you want to read about a guy who was into everything, Laplace is the guy to read about. And lastly, I believe we've got Kepler and Encke. Kepler was the guy who took all of Tycho Brahe's calculations and determined the equations for the orbits of the planets in our solar system. And those equations are still valid today. He was also a little crazy, and he kept playing with all these perfect shapes, trying to get one to fit inside the other. And I don't know, a lot of really smart people are also a bit crazy, and he was one of them. And Encke was a mathematician, astronomer. He was known for actually figuring out the orbit of comet Encke. So he didn't actually discover it. It was discovered about 6 or 7 times over 60 years before him. And he noticed the pattern and predicted the next time it would be visible, and he was right on. So that's who they decided to name the comet after. It's a very short period comet, less than 4 years. So I believe actually it's either going past now or just a little while ago, but even if it isn't, it won't be long. Here's an image from the net showing the moon at the 11th day during its lunar cycle. And this would be right about the time that Joanne took all her pictures. And starting at the top, you can see Sinus Iridium and Cape Laplace and the Sea of Rains, and then Copernicus right down below, Kepler to the left, and down, way down, like the friendly giant, look far, way down. There's Tycho, and below that is Clavius right there. So Depending on what you want to look at, pick your day of the lunar day, like the phase, and make sure that if you want to see a lot of detail, make sure that the terminator is close to what you want to look at, and that'll give you the best relief when you're looking at the geography. We also just had a Moon-Mars conjunction and occultation. Now, unfortunately for us in the upper hemisphere, it was only in the lower hemisphere where Mars disappeared behind the moon. So all we had was a conjunction. The closest it got was about 1 moon diameter away, so half a degree. And here's a picture from space weather for a fella in Florida taking quite a nice picture. And Mars is very bright. And in fact, it's only going to get brighter for the next month or so. So this is awesome time to be looking at Mars. This is from Argentina, so southern hemisphere. And there's a nice shot, a very nice shot actually, with Mars very close to the limb of the moon there. And I really like this one because it's from BC. It's looking east towards the mainland. You can see the moon there on the right. I hope my cursor shows up. And just above it's a really bright dot. That's Mars. And also in this picture, you've got a lot of stars to look at. So there's Capella and the kids in Auriga. Up here is the Perseus Association with the Perseus Arms and Algol. There's Triangulum over here and Aries over there and countless other stars there, which is a nice shot considering it's not absolutely really dark yet. So I really like that one. That was from Space Weather as well. So at this particular time, we've got really a parade of the outer planets. So that's all the planets outside the orbit of the Earth. And if you're going to study them with your telescope, start in the west because obviously they're going to set the earliest, but this is at 10 o'clock at night. And Jupiter and Saturn are still very close together and are only going to get closer. By the end of December, they'll be extremely close. But start there and work your way east. And when you get to Neptune, Neptune is not naked eye visible. You need binoculars. It's about magnitude 7.8. It's only 2.4 arc seconds across. So when you find it, if you find it, it's going to be a nice greeny blue looking star, like a bloated star. But I personally have never seen a disk. But if you can see it as a disk, good for you. It's very far away. If you've got really high magnification and a tracking mount, try for Triton. See if you can pick it up. It is visible. Even with a medium-sized amateur telescope. And further east is Mars. Mars is still low at this time of the evening, but by midnight, it's nice and high. As I was saying, Mars is approaching opposition, which is in mid-October. And this is the best apparition of Mars for the next 15 years. So every 26 months is when we have a opposition with Mars, when it's at its closest. But unfortunately, due to the variables in the orbital geometries of the Earth and Mars, the closest approach can be quite different from one time to the next. And this particular time, Mars is at about 22.4 arc seconds, which for Mars is really big. And hopefully the forest fires will stay away and all the smoke from the west. And hopefully this time there will be no dust storm on Mars at the same time. And just a bit to the east is Uranus. That one is naked eye visible right now at magnitude 5.7. It's a bit bigger. It's around 3.8 arc seconds, which means that if you've got really steady conditions and a telescope and lots of magnification, you should be able to see a disk, but it's going to be a very tiny disk. And if you're really lucky, you might pick up some tiny pinpoints of light and try and identify at least a couple of the moons. It is possible. And now a quick go around the sky. So starting in the west, and I'm mostly going to talk about globulars because we're running out of time to look at globulars, and they are fascinating and they're easy targets in a light polluted sky. Well, compared to others anyway. And if you're just starting out learning the constellations and then using the constellations to find globulars, this is where you want to be, because in the winter, almost all the globulars are gone because we're looking out towards the edge of the galaxy instead of across the galaxy, which is where most of them are situated. So let's start in the west at Arcturus with Boötes. there, I call it the kite. And M3, that's a fantastic globular. It's beautiful. And it's actually fairly easy to find because you start with Arcturus and you draw a straight line to Cor Caroli in this little tiny 2-star constellation of Canis Venatici. And all you do is divide the distance in 2, put your binoculars there, and it's going to be right there. And then you can put your telescope on it. Working across, you get to M5 under Serpens. This one's a bit more difficult to find because there's not a lot of bright stars really close to it. But at this particular time, if you take the brightest star in the middle of Serpens there and go straight down, you should run across it with binoculars. And notice I keep saying binoculars because that's how you find these things to start. Up high, you've got M13, the great globular in Hercules. And that's always awesome. And the way to get there is start from Arcturus and the kite and go up the left side, skip over to Corona Borealis and zip around the loop and go straight up. It'll take you to the corner of the, what I call the Dixie Cup of Hercules, which is just this oddly shaped 4-sided piece here. Now, while you're doing that, have a look for M92, because if M13 wasn't there, M92 would be a showcase object in the sky. So a lot of people skip it. I recommend you have a look for it. And working over towards the southwest, you're going to run into Ophiuchus. This is a huge constellation. It's not that easy to pick out. You have to take your time. And the way I sort of look as a guidepost is I look for these 2 equally bright stars here and then start working around the outside. And the ones I'd be looking for are M10 and M12. Because you can find either one and then just flip across a few degrees to the other. If you're really feeling lucky, look for M14 over here and 107 down there. Now, all these ones that are really low are going to be tougher because of light pollution. As Jim Walmsley would say, there's lots of schmutz. So you're going to have to really try for those. Now we're looking due south. By the way, this is all at 9:30, so it's not late. Astronomical twilight ends about 9:20, so it's truly nighttime by this point at 9:30. So that's great. Due south is Saturn. There's Jupiter there. And below Saturn, almost directly, is M55. Now, Denise has been looking for M55 for a while, and I know she's still going to be looking for it, but she will find it eventually. And if you go back to Saturn, you can go a few degrees to the east here on the left and get M75. And if you go up a few degrees, you're going to run into Barnard's Galaxy, which has just on the edge of it, a really nice planetary nebula. So a very tiny planetary nebula. And if you want to skip over into Capricornus here, you've got the Saturn Nebula, which fits in with the whole Saturn idea, and M72, another globular. So there's lots and lots to see just in this area. I mean, you can go crazy. Obviously, the Milky Way is right there, right? Now, another one globular most people don't bother with or know about is this one in Delphinus, C47. So it's a Caldwell object. These are kind of like the objects that Messier and a few other people missed. And so these are normally all bright objects that just were not found at the time. So if you can get, if you can get to Delphinus and just come straight down from the tail of the dolphin with binoculars, you're going to hit it. And then I'm going to go to the next slide. Okay, so in the middle of the screen, you've got the Great Square of Pegasus. And that's what I use as a starting point to get these next couple of globulars, which are M2 and M15, and also beautiful ones to look at. And the way you use Pegasus here is you come down to the Markab and you follow this line of fairly bright stars, probably about magnitude 3, 5, or 4, out, and then up to the next bright one, Enith. And then if you take half this distance between the last two stars and go straight up, you'll run right into M15. So that's an easy one to get. For M2, which is just to the east here, you take the two stars here and you shoot out the same distance and you're going to be right in the ballpark of M2. And these are both really nice globulars, worth the time to take to have a look at them. Of course, if you scoot across from Pegasus, you end up in Andromeda. And of course, there's always the Andromeda Galaxy and the Triangulum. Triangulum, you need darker skies, and binoculars are the way to see it, not a telescope. Almach at the end of Andromeda is a beautiful double star. don't miss that one for sure when you go looking. And around to the north, obviously you've got Perseus and the Perseus Association, and then you've got Cassiopeia. There's lots and lots and lots of stuff to see there. But what I wanted to look at was Polaris, because Polaris is a double star, and Polaris B is, I think, about 4 or 5 magnitudes dimmer than Polaris. So it looks like a tiny point of light just off to one side of Polaris. But it's worth a look because most people don't even just know it's there. And what else do we have here? Well, of course, the Big Dipper is low in the sky, but maybe not right now. But as the Big Dipper gets higher in the sky, look in the area between Canis Venatici and the handle of the Big Dipper. It's full of objects to look out, Messier objects, all kinds of stuff, including the whale and the hockey stick. If you've got an 8 or maybe 10-inch Dob or bigger, you can actually see the whale and the hockey stick, which is really cool, little galaxies there. And directly overhead, most of us don't like to do that because it hurts our neck. But if you do happen to look directly overhead, you're going to see Cygnus up there in the Milky Way. To the left, you're going to see Vega with the Ring Nebula right in between the 2 stars here, like almost dead in the middle. And if you really want to have a challenge, look for M56. It's another globular, which would normally be quite easy to see, but it's in the Milky Way. It has the Milky Way behind it. And so the way to get to it is to take this corner star right here in Lyra, look for Albireo, make a straight line, divide it in 2, and put your scope there, and just move your scope around until you maybe catch a view of it. I have found it. It took me a while, but you can get there eventually. And lastly, on here, here's the head of Draco, the dragon. Look for the dimmest, most uninteresting star in the head, which is this little jobby right here. Put your telescope on it and you'll see what's called the headlights, which are 2 stars, which are almost exactly the same magnitude, nice and bright as well. And it really does look like a set of headlights coming at you in the night. So that's it for this month. Thank you very much.
Thank you, Matthew. Absolutely wonderful. Matthew always does a fantastic job, and please check into the club newsletter, The Event Horizon. Matthew has a column there, of course, each month, and incorporates a lot of different material than what he presents here in his presentation. It's very worthwhile checking. So wonderful. Thanks, Matthew. Just excellent.
You're welcome.
Sue, do we have anything pending before I wrap up here with some final announcements?
I see nothing pending and nothing in the chat. So you're good with final announcements.
All right, wonderful. So just a couple of last minute reminders. Not next week, the week after will be council meeting, done in an online Zoom format, just like this. So councilors, remember that. Next month, at our October meeting, we have Dr. Hilding Nielsen from the University of Toronto. He studies stellar physics, and I'm very much looking forward to what he has to say. Between then and now, we will pass the deadline for the calendar. I reminded you before, I'll remind you again. Calendar deadline is September 30th. Don't forget that. If you're interested in joining council, that will happen next month as well. Volunteers are welcome. Please feel free to contact me, chair@amateurastronomy.org. Tonight, I certainly, I'll also remind our door prize winners, Anne and Jeff and Peter and Mario, to all get in touch with me directly, and we'll set up a time when we can put prizes into your hands. I want to thank Sue and Doug and Chris for doing another stellar job behind the scenes, getting everybody into this meeting and out, getting all the information flowing. Wonderful. Thank you to all 3 of you. Sue, fabulous job as always. Maya, so great to have you back in the program. Delighted to see you. Thanks for taking care of the door prizes there. Matthew, thank you for your presentation. Always excellent. And a big thank you to Sean Ford for coming out tonight and giving an absolutely delightful presentation. So informative and so well done. I can't thank you enough, Sean. Please, everybody, all right, remember that because we're not gathering together, it means we are not gathering items for the food bank, but that doesn't mean that you can't make a donation directly. Please don't forget to give to those in need. Thank you one and all for coming out tonight. Very much appreciated. Great to see you all, and we'll see you all in October.